will no doubt flash up a message on all of your devices. So welcome, good morning or good afternoon, everyone, depending on where in the world you are. Welcome to our weekly call. We've got two things we're going to cover today. We're firstly going to kick off with DOE fingerprinting. So this will follow on from the call we had a couple of weeks back, where we looked at fingerprinting and DPI as it applies to encrypted DNS. And any of you that were on the call may recall that Brett kindly volunteered Henri, hopefully with his foreknowledge, to also share some thoughts on the same topic. So we'll cover that first, and then we'll move on to DNS-based data theft, which again, Hamilton suggested one of his colleagues, Daniel-Paolo, who's also on the call, will take us through some findings on that topic. So let's start with DOE fingerprinting, and then we'll move on from there, and then time permitting at the end we'll cover off any other business. So Henri, firstly, over to you.
All right. Thanks for inviting me on. Thanks, Brett. So I've got some slides. How do I?
Okay, let me see. You should be able to screen share.
Okay, I'll share screen. Okay. I have to change my, oh no, that's not good. I have to jump off the call because it's not letting me, I don't have given it permissions to share my screen yet.
Or you can email it to me if that's easier, Henri.
I think it'll be easier just for me to jump off. I'll wait. Sorry guys.
Fine, do that and then jump back on. Hopefully that'll be okay. I'm guessing that's the joys of an Apple device.
Yeah, the Apple have tightened up on that in the last release, didn't they?
Yeah.
Hi, Andrew.
Hi, Zaid.
How did you enjoy the World League?
Well, I enjoyed it. Hopefully those people that came onto the workshops I was involved in enjoyed it even more. Busy week, mind you, or busy 2 days.
They were very interesting. I liked the workshop that you were in one of them, I think. One of the workshops I attended, you were on one of them.
Yes, I think so too. Workshops 3 and 5 were the two I was mainly involved with. Right, let's just see if Henri has made it back on to start the presentation. Not quite yet. This is where I need some music to play in background. Ah, he's connecting back on.
Sorry about that.
That's okay.
Okay, now if I do that, share.
Perfect, that's working.
And what are you guys seeing? Are you seeing the presentation or notes or both?
Presentation.
Presentation.
Okay, good. All right, yeah. So detecting DOH traffic. I'm aware you had some encrypted TLS analysis presentation earlier, and so this is sort of a specific use case of that. A little bit about me before I start. So my background is in electronic engineering, focused on signal processing, and I thought I'd end up working on circuits for the rest of my life. But then I happened on a small startup called Darktrace, ended up working as a security analyst there, experienced a few hundred different types of networks, hands-on analysis, then moved to R&D at Darktrace, working on some new features for the product. And then in end of 2018, I moved for a full-time research role at Nominet, security research. I try to sit between cybersecurity and data science. And now I explore new features and possibilities for the Nominet's government PDNS and its corporate NTX product. I started working on DOH research in early 2019. I was actually asked about it in my interview, which was amusing because it turned out the interviewer didn't know either what to do with it. And at the time, there wasn't too much in the public domain. Obviously, since then, there's been quite a few published pieces of work on it. To be honest, I haven't looked into it much since summer 2019 because the project was kind of frozen because of changes in our product scope. So, but hopefully I can still share some insight that I might have gotten. Okay. So just overview of what I'll cover: DNS over HTTPS, why we want to detect it, focusing the problem, what information are we going to give ourselves, where are we looking, some scenarios of different DOH use and how that might affect how we can detect things, how can we model DOH traffic, and so what conclusions and recent developments. So let's look at just brief overview for everybody comparing DNS resolution. And it's basically the easiest way for network managers, users to access the control plane. So that allows split horizon DNS, log monitoring, RPZ, all these tools are available. And there's an increased encryption of data plane communication. So SMB version 3, encrypted, HTTP to HTTPS, SMTP to SMTPS. So more and more data is being encrypted in transit. And that puts a lot of existing security tools in a difficult position, especially if they're dependent on packet inspection. And that's why the control of the control plane becomes even more important for security, because visibility in the data plane is lost. So security is generally thought of in communication terms, confidentiality, authenticity, and integrity. So checking no outside party can see the contents of conversation, that all the parties are who they say they are, and that none of the messages are tampered with. DNS 53 or standard DNS, weak across all three basically. And that's why the encrypted DNS protocols have been brought up. DOH then takes off-the-shelf TLS to provide all three. But what DNS 53 lacks in those, in terms of secure communication, it provides in transparency. So upstream issues can be identified downstream through monitoring and management. And as you can see, it doesn't really resolve those upstream security issues. As such, the decision on use of DOHs and its management is really important to network owners. So that being like, if I install an application, I want to know, is it going to use DOH and whose server is it using, which is pretty obvious. So where can we look? We can look on the client. We can look passing through the network, decrypting proxy. And obviously decrypting proxy easiest solution for a network, but obviously that has its own complications. So I won't be looking into that. I won't also be looking at client side information data. I'll be focusing on information available as a third party in the middle for example, tapping a network switch or firewall. So what information do we have available? A lot of the DOH clients need to get their server IP address from somewhere. Either it's hard-coded or it's has to be queried using standard DNS. So we can have that query name IP address if it's available. TCP IP layer, we can get the client and server sockets. And then at the TLS, we have the handshake. From that, on both sides, we get SNI. We get the application layer protocol negotiation. So we get what is the requested following protocol. So is it HTTP or is it something else? Good way to filter out potential non-DOH TLS traffic. And the JA3, which is created using the client hello fields. And on the server side, we get the certificate. And in the middle, we get record size, record timing, and TLS record directionality. Just briefly on JA3, I know you guys have heard about it before, but basically we take fields from the client hello, and then we turn them into a hash, and they're generally unique to the encryption library, but they map one-to-many applications. There's also the server side JA3S, but in this case, because the HTTP, the DOH server usually sits behind a standard HTTP server, it doesn't really, we'll just get the J3S for that, so it doesn't really tell us much. I've actually done some work on J3, so looking at the clustering using the actual underlying values, and there's what you might call hereditary effects, where applications which have, let's say, so Chromium-based browsers will cluster together based on these field values. Computers versus mobiles can be split using these values without actually having seen the specific hash or that set of values before. So there's some possibilities there for identifying DOH clients. So when we look at how is DOH being used, there's a few questions to ask. Do we know the end user application? Is it Firefox? Is it, is it a DNS proxy? Does the end user application resolve DOH server using DNS-53? Again, that tells us a lot. In Firefox, by default now, it uses DNS-53 to find the IP address for the DOH resolver, but that can be set as a bootstrap address, and so then no query is done, leaving the network pretty blind to the traffic. Does the DOH server share host name or IP address with other services? That could make things tricky for blocking or identifying. If Google moves its DOH server onto the same IP as YouTube or another CDN or something, then that becomes tricky to identify if there's a lot of mixed traffic going to an endpoint. And then also if the end user application generates purely DOH, that's versus producing mixed TLS traffic, that affects things. And is that one-off query or regular resolution? So are we talking about a piece of malware that does a one-off DOH query, or is it performing regular queries like a Firefox application? So Firefox, we can identify the default servers from multiple places. We can see it from the DNS resolution if that's enabled, from the server name indicator, from the server certificate, etc. And we can identify the Firefox version number using the JA3. Then a piece of malware which performs a single DOH query, that becomes a lot more tricky. Also, the static pieces of information, we can, I think until recently, Google and Amazon allowed domain fronting. So the SNI, we can place a fake SNI, and I tested this yesterday, and Google still allows it for their DNS.google.com. I can set the SNI to anything I want, and it'll still happily accept my query. This curl command here used to work, but it no longer works. Maybe with some fiddling, something like it could work, but that's a nasty little bit of code there, because it will allow to everyone outside, it will look as a query to google.com, but then only once it's unencrypted in the HTTP field, it's a DNS.google.com query, which then gets forwarded on server side to DNS, to the DNS server, which makes it very tricky on the outside using the static fields to identify. So let's look at some of the dynamic features that are available to us. So again, size, direction, timing, we can encode those into two feature vectors. The size, we can encode the directionality using positive, negative, arbitrary which ones you choose. And timing, I actually looked into time delta between records. And so you get those two vectors there. So if we look at how that looks visually, this is the first 100 TLS records for a connection to DNS.google and Facebook.com. And we can see the behavioral differences are pretty clear. And so that gives us hope, at least for these sorts of continuous DNS resolution services. Like this was done using Firefox nightly back when the standard Firefox didn't allow for DOH. So what models can we use? I started off using an RNN, a recursive neural network, and that did not, but it should perform well. It's intended for sequential data. It's generally has difficulties with long time spans. And that's not an issue here because we're talking about relationships in the between packets in sequence, not over long durations. But it doesn't perform well on small data sets, which is what I was generating mostly my own data, driving my own data, and so getting that it can easily overfit. So then I looked more into using more basic crude models. And that would allow less overfitting and really get down to the underlying behavior of DNS in TLS rather than specific client application or context. So I worked on a Markov model, or built a Markov model. You lose the time dimensionality, you only get sequence in this case. I mean, you could encode it, but I didn't. The dimensionality, so here we have the probability matrix transition from the different states, and the states being the, in this case, the record length that we're seeing in the connection. So and we can see the dimensionality is the sort of the memory of the chain of records. And so in the figure there, it's a two-dimensional matrix. I used a three-dimensional to get a little bit more context. The more dimensions you add, the sparser the matrix, the weaker your the performance is, depending on the amount of data. The more data you have, the more full your matrix gets. the sparsity can also be reduced by bucketing the states. So rather than using each record length as a unique state, you can group them. So what I did was, if we look at the distribution of a scalar value like record length here, so this is using training data. I trained, I believe this is DNS Google, the distribution of packet lengths for connections to DNS.Google. And we can see a test case here using 50 packets, and it fits quite nicely onto the distribution of lengths that you would expect for a DOH connection. And using that distribution, you can create boundaries which are much more effective in defining the DOH. So, okay, yeah, short demo. So I don't like doing demos live, so I took this video earlier today. So something I prepared earlier. It's got a nice bit of sound to it as well. So launching Firefox. So in the back, I have a small utility which is taking my wireless traffic, parsing out the packets, and deriving some data. So we see here all of the connections, and there in red, you see it's already taken out the 104, I believe that's Cloudflare, and it's recognized that in the first 100 or so packets to be DOH traffic based on that pattern. So you can see the Markov score is high, record length, so that's the distribution, is high, and so it's been classified. And then we can see other connections here, BBC, some Chartbeat, and those are producing low scores across these metrics. Okay, yeah, so how are we doing on time? Can't actually see a clock on here. Okay, I'm running a bit over. So yeah, false positive rate. I ran the model on about 1 gigabyte of network data because obviously I was worried about missing some type of data because I was mostly using web traffic. So I was worried about application traffic with beaconing type activity. Actually, using these models, underfitting and capturing false positives isn't really the issue, it's overfitting, which is really easy to do. So you're fitting to specific contexts of TLS activity. So for example, timing, it's dependent on so many things, which server you're using. So you're, so the attempt should be to build models of TLS activity, which are modeling the underlying behavior of the protocol. So in this case, DNS, rather than the specific context. So application server, network, etc. More data, more complex models, more data. I think RNNs would be very powerful in this case. But you need a really good data set for that to deliver and not overfit. So I used 4 different DOH servers, Google, Cloudflare, Quad9, and can't remember what the 4th one was. And all driven using Firefox traffic. So that's looking at research that come out since. I saw a nice little article where they were identifying specific web pages from a known set of web pages using similar techniques. The interesting thing about it was they were so they were looking at nation state adversary type attacks and seeing if blocking could be done even with DOH, and they found that theoretically it's possible with some caveats. And they were recommending padding the TLS packets to a specific size, stopping anyone from being able to see, glean more information about the contents of the DOH. And ironically, this would help our case in identifying DOH, because if they were all, it would be very unique for the whole connection to have a consistent packet size. So it would probably make a lot of two sort of groups happy. It would make the group who want to stay private happy, and it would make the group wanting to identify DOH on their network happy. So that was quite interesting. And I think that's it from me. Any questions?
Thanks, Henri. So does anyone have any immediate questions from that? I'm conscious you gave us a very rapid run through some complexity there, but I think covered the key points. So I see Jim has his hand raised. Jim?
Thanks, guys. Very interesting presentation. Two quick questions. How does your research activities here, Henri, compare with the work that was done by some researchers who presented something at the ANRW session at the ITF meeting last summer in Montreal? They were doing some kind of similar traffic analysis to actually identify encrypted DNS traffic based on things like the packet arrival times and other patterns of behavior. And
so,
sorry.
If I'm, do you want to ask both of your questions, or?
The second question is that if you're relying on packet length to try to do some kind of fingerprinting here, to what extent is that going to be thwarted if people use padding?
Yeah, so first question, I think, I'm not sure which research you're referring to, but it might be that one I'm pointing to right here, where they're looking at, and yeah, there's quite a few, I mean, there's only so much you can do with encrypted TLS. So there's, I think there's a lot of people working on very similar things, approaching it from slightly different angles, but a lot of overlapping work. I mean, this paper is going back to early 2000s, looking into TLS feature extraction, very similar lines. I think what would be unique is trying to really fit it specifically to DOH, which gives you a lot more possibilities. By making the model more crude, you almost you end up getting better results in terms of not overfitting to a specific context, which is what I think a lot of research I've read has had issues with. So if you switch from one, let's say Firefox to a DNS, one application to another, suddenly the features changed if the models are too fit to a specific training context. And second, I've forgotten your second question. Sorry, Jim.
About padding, I think.
Oh yeah, padding. Padding. Yeah. So if the padding, so in the paper I mentioned, they suggested constant padding. But I guess if you had, I think, yes, if you used any kind of pseudo-random padding, that would be unique in itself, because traffic isn't pseudo-random. It would fit into some, I mean, whatever. I mean, I guess you could do padding, which, if you wanted to be mean about it, and you could create padding patterns that fit specifically to look like general web traffic, so fit all the statistical properties of web traffic. But yeah, that would be quite mean. But yeah, all of these would require adaptation if padding was placed to the protocol.
Obviously, if you were a malware writer who wanted to use DOH, you would be mean about it, right? Once you found out that people were detecting you, you'd start being mean about it.
Yeah. So I mean, like with JA3, so people used to use user agents to identify malware. Malware creators quickly started mimicking browser user agents. Same with JA3s, but generally malware creators are quite lazy. So with JA3, it's possible to mimic, but it's a lot more work. It's a lot more work trying to change your encryption libraries compared to a string in your HTTP field. So that's one of why JA3 is a little bit more robust, I guess. And the same in this case. I mean, yeah, I think that's
okay. Thanks for that, Jim. We've got time for one more question, then we need to move on. And John Todd has his hand raised. So, John.
Hi. Interesting research. I would be interested. It seems like you're looking at DOH kind of by itself in a vacuum, or does your research actually look at the query response patterns of different IP addresses from what you expect the DOH server to be? In other words, is it possible to identify DOH not simply looking at the streams individually, but to look at the pattern of context specifically for web browsing, but potentially for other traffic as well?
Yeah, that's fitting it into that sort of larger contextual behavior is actually probably would be the, at least for browser traffic, would be the way to go. So yeah, that I agree with you. That would probably be a much more, it's a little bit more complicated, but that's definitely a possibility I could see, because obviously if you're looking at browser traffic, you know that each connection is generally preceded by a DNS query. So if you just look at the pattern of packets going in and out, you should be able to see which channel that those, I mean, that information has to pass through some channel. So if you know that, you can just look for it. So yeah, I agree with you there. One thing is that I think just two quick points. One is there's a fear of sort of malicious DOH servers. I think that's unfounded. There's no point for a malware creator to create a DOH server that serves up, that they use exclusively for malicious purposes. I mean, the point of using DNS is so you have a mobile infrastructure. That just defeats the point. So they might as well use the biggest resolvers out there to fit in. And yeah, and the one-off query problem, I don't think has a solution. So the only way to solve that from a traffic basis would be to use this analysis to identify a list of available servers and DOH servers.
Thanks.
Okay, thanks, Henri. And I see Jim has posted some links to some papers in the chat, which may be of interest to you, just with the sort of referencing back to those presentations he mentioned, if that's useful. Okay. Fantastic. Well, look, it's a fascinating topic. I think we've only really scratched the surface in the available time, but I think really appreciate making the time to actually sort of give us that introductory sort of run through. And I've no doubt we'll get some sort of follow-up questions after the call. So thank you very much, Henri. But because of time constraints, we will now move swiftly on, and I suspect we will run over the hour realistically. But if I move on, we've got Daniel-Paolo Streitbürger from Rohde and Schwarz, who's joined us. So Dr. Daniel Streitbürger, I should have said. Apologies. So welcome, Daniel. I have some slides for you, so if you bear with me just a moment whilst I...
or I can share them, it doesn't matter.
Whichever's easier for you, Daniel.
I can try it. Let's give it a try.
Okay, do that. If not, I've got them queued up ready if need be.
Oh, that's a pity. So, I hope you see everything.
That's working.
Nice. So, I hope everybody can hear me. Yeah, thanks for the kind introduction, and special thanks to Andrew Campling for giving us the opportunity to present our current research in the field of DNS protocol exfiltration. Today's talk will be much more about a data analyst's view on the DNS data and how it could be misused for data exfiltration, rather than the technical details of DNS protocol or the legal implications and regulations you discussed last week. So, but I still hope that it's maybe interesting for you. When I compiled these slides, this was already a couple of months ago, I intended to address a completely different audience. So I managed to change them heavily for this presentation, but the overall topic, the overall theme of this presentation is still valid, because it says that, or it's the idea of, can we prevent data theft? So this is the whole idea, and I will come to this at the end of the discussion. We'll come back to this. So let's start with the presentation. From a very simplistic and general perspective, every company of a network, every network of a company can be seen as I have depicted here. It's some computers, some servers. They are all connected via switches, routers, and so on and so forth. And eventually they are protected using a firewall to protect the inside world from the company, a network from the outside world to the scary, scary internet. And this is a very simplistic overview, but it should be sufficient for the motivation. And if you consider that the firewall has a very, very detailed view on the traffic, and it by simplicity just simply drops connections and protects the inside world from the outside world, and it only allows DNS or HTTPS, it's quite obvious attackers are still able to misuse the DNS protocol for their purposes to exfiltrate data from the internet, from the company. This isn't only an academic problem, it's a real world problem. And when I woke up this morning, I actually wanted to show you this slide from my presentation, but yeah. Sorry for that. Exactly. When I woke up, I wanted to show you this presentation, but Andrew Campling wrote an email a couple of hours ago, and he outdated my slides a bit. So I managed to integrate the new information, and it's updated quite nicely. But I want to, first of all, jump to the first examples I show here. It's from Home Depot. It's a retailer in the US, and it's from 2014, 2015, something around that, where they have been targeted by attackers, and within a time range of 6 months, those attackers were able to exfiltrate 56 million credit card numbers. And the very same thing happened to Sally Beauty, a retailer for beauty articles, with only 25,000 credit card numbers. But it's still tremendous reputation loss for those companies. And considering the fact that this happened in the US, we can all safely assume that there were financial damages as well. Regarding the newest information from Andrew, many thanks for this refresher information. It was really in time. In a survey from the Global DNS Threat Report, 79% of the companies confirmed that they were targeted with DNS-related attacks in 2019. And 17% of all those attacks were DNS tunneling or DNS exfiltration related. This is quite a huge number, I guess. And considering the fact that there's approximately 1 million in average for the US dollar in average per successful DNS-related attack, which the company has to somehow invest either in legal cases or in updating infrastructure or so on. It's quite a substantial amount of money, and that's the case on. That's the reason why we think this is a real case scenario, real world scenario, and not only an academic one. So enough for the motivation. Let's just very, very shortly go to the exfiltration. So we assume that we have a computer and an infected PC in the company network, and we have a target server in the internet, and they misuse the DNS protocol, basically using the subsegments of the query name of the DNS, so the Q name field of the DNS. And what does it look like in the end? So it's like gibberish. It's like random noise, basically. Definitely not human readable. There are long strings, URL safe, normally with characters and digits and maybe even special characters within. Those DNS exfiltration attacks tend to have a very short domain name to save bandwidth, because the Q name is only 255 bytes long. So these are the information, and this is the way an exfiltration will take place. So arbitrarily everything, or not arbitrarily, but virtually any information can be exfiltrated. And by bare eye, so just by visual inspection, we already see that this is somehow fishy. And this is the reason why we said, okay, it should be possible to train something or to make something happen that we can detect those exfiltrations. So exfiltration is encoded data, attacker domain, and some top-level domain. Of course, this exfiltration can be easily extended to a two-way communication, and in that way that the DNS response is misused again by the attackers, and they can infiltrate data towards the infected PC, download some worms, Trojans, or whatever they deem to or wish to. And this is quite obvious, so that the DNS protocol can be very easily and effectively used to exfiltrate data. And this often happens under the radar without noticing of any technical staff or administrators, simply because the traffic isn't monitored thoroughly. This should be sufficient for the motivation. But how could we detect the DNS exfiltration? So we made a quite comprehensive research about what has been done already, and the literature was full of machine learning. So they basically shouted at us and said, do something with machine learning. And there are numerous papers all already having quite good results, and they strengthened our confidence that we will manage to do something as well. So machine learning is definitely something which is much more in our field, or in my data analyst field. And machine learning methods there is a multitude of them, starting from decision trees, support vector machines, k-nearest neighbors, and so on and so forth. And this is only a very small excerpt of methodologies we used and we are able to use. Our main problem, or our biggest challenge actually, is not the algorithm itself, but that we have to somehow seamlessly integrate our solution into an already existing environment. So we normally have this field, or the setup that we have some kind of a network on the left side here, generic IP traffic, and then we have the net sensor, the Rohde and Schwarz net sensor, which is installed at important points at the internet, at the network, which passively looks on the data and aggregates it towards the Net Reporter Plus, which then somehow visualizes this gathered information, so that the customer has a better impression of what is happening within his network, and gets an idea how the customers are behaving and how the users use his network or their network. And we intended that our solution seamlessly integrates into the Net Reporter Plus solution, in that sense that the customer gets an alarm or can see per customer or per subscriber in the internet or in the network, which is monitored, if it is infected by some exfiltration software or if it is not. Data acquisition, of course. Every machine learning algorithm requires some kind of data, and we read through all those articles we managed to find, and we decided that we will create our own data sets for our own analysis, and that's why I split it up. Split the data sets into 3 parts: the normal DNS traffic, the DNS exfiltration traffic, and the DNS tunneling traffic. And we automatically generated numerous DNS records. I will come to this slide later. And we channeled it through the intended environment. So we channeled it through the net sensor and through the net reporter and made our analysis with the aggregated information we got. The DNS traffic itself was around roughly 1 million websites we automatically visited using several drivers like Firefox, and Chromium, and others, which in the end resulted in something around 3 million DNS request response pairs. Whereas the malicious DNS traffic is roughly 1 million per exfiltration and tunneling. We tried to use software which was already available at the internet, and we tried to scrape the internet as good as possible, as long as we stay within legal borders, let's say. And we even revived a couple of tools to make them running on the servers and so on. But in the end, we had this quite good-looking data set for our analysis. So, of course, first of all, we were curious. We looked at the data via manual inspection, and we identified a couple of parameters which were quite interesting, all DNS specific, of course, like query type, response sizes, answer counts, and many more. And at the very end, we, in an iterative procedure, we manually crafted a feature set of around 21 attributes. Today's presentation is specifically 21 attributes per each DNS record we created. And all those features are stateless. So we do not depend on any DNS record beforehand or afterwards to identify whether it is exfiltration traffic or not. As I want to show you the results from the random forest algorithm, and I wasn't sure if you are all aware of how random forests work, I decided to give you a very, very short introduction into decision trees, because the decision tree is basically the predecessor of the random forest. So I will quickly guide you through it. The decision tree is exactly what everybody has already been doing, I think, their whole lives. It's a big if then else clause, and if you have a path A or B, you follow B, and then you have another decision and you follow B1 or B2, and then maybe you are at B2, and then you have C and D and many other levels, until the end you get to some kind of a decision, and you say, okay, this is my final answer. And this is the very same thing the decision tree does. It basically tries to separate the malicious DNS records from the normal DNS records using a split algorithm. Normally it's something like the Gini impurity score or the entropy. It really depends on how you configure your parameters. But there are kind of disadvantages and advantages of this decision tree. So they're basically very easy to understand. So you can normally quite easily understand what they are doing, and they can be easily rolled out into plain C code. So this is quite important if you have computational power, or if you have timing constraints like we always have in the field of DPI. But unfortunately, it easily overfits. So you have to be very, very careful about your parameters you use. So what's about the depth of the tree? So how many nodes until you finally come to a leaf do you will have, or how many leaves will you have in your tree? All those parameters decide how much your decision tree will overfit, and simply memorize the entire input data and training data and fool the data analysts and saying, I have learned everything, but in the end, in real world, it hasn't learned anything. It just simply memorized the complete training data, and this is normally then seen in the testing phase that the accuracy is, yeah, pretty low. And to overcome this problem, the random forest comes into play. The random forest is basically combines a multitude of decision trees, so it's something around 10 to hundreds or even 1,000 decision trees, and trains each of those decision trees with a slightly different set of observations. So this includes a bootstrap sample, so it's only maybe 10% of the input data, and a subsample of the considered features. So in our case, we had 21 manually crafted features, but not a single decision tree sees all of the features, but the first 10 decision trees maybe only see 10 of those 21 features, and the other decision trees see 8 features, and then again only 15, and so on and so forth. So none of the decision trees is ever able to see the entire data set and to memorize the entire data set and fool the data analyst in the end. And the decision trees in the very end just simply make a majority voting. So 51%, for example, say that it's malicious, and then it's malicious. So this is the idea of the random forest, very, very, very quickly, very, very roughly. We did our analysis, and we were quite pleased, and it was completely in line with the literature. But we were a little bit concerned that we did everything wrong. That's the reason why we took a closer look at the most important features. So which kind of features did the algorithm, the random forest, learn to differentiate that he has seen a malicious DNS record compared to a normal DNS record? And the top 5 features were the request size of the DNS record, the number of dots in the queue name, the number of digits, the entropy, and the type of the DNS query. And basically all those information totally fits within the idea. So I have here a graph where we show the number of digits with the frequency count. In blue, we have the normal DNS, and in orange, we have the malicious DNS record. And you can see that basically from, yeah, let's say 25 maybe, or 20, none of the normal DNS records has more than 20 digits in the queue name, whereas the malicious DNS records, they have even 255, obviously. So it's quite easy for the random forest to make a split here, somewhere around 20 or 25, and say everything above 25 has a higher probability of being malicious. The very same thing is for the entropy. So there's a very sharp split here around 1.8, where you can say that everything above 1.8 entropy has a very high probability of being malicious, whereas everything below has a higher probability of being a normal DNS record. So taking these into consideration, we were quite convinced that we trained the right parameters, that the algorithm has learned the right parameters, and that he has trained or understood the generic pattern which is needed to identify malicious DNS records. And the accuracy was quite surprising for us, because it was even better than compared to some papers. It was around 99.9 something 7% accuracy, and we trained it on only 140,000 records and used the remaining ones for our testing. So approximately 3 million for normal DNS records and 700,000 malicious DNS records to get those, quite good results. And of course, these are not, or this is not everything we needed to check. We had some curiosity and some concerns about the performance. As we did quite a lot of analysis in Python, which is more or less a state-of-the-art programming language for machine learning, we have a much higher throughput rate or requirement on throughput rate. So we implemented something equal in Java and made a comparison, a speed comparison in messages per second we can process. And there's quite a huge difference between Python and Java. So with Java we get approximately 140,000 records per second, and these tests has been executed on a single PC with a single core. It's only a laptop at my desk, so we were quite convinced that we can easily achieve even higher numbers with a little bit more on better hardware. So in the very end, we had this three things. We were convinced that the algorithm has learned the right thing. He is quite accurate in what he's doing, and he's sufficiently fast in doing his predictions. So to take a quick recap and an outlook, what we will be doing in the next couple of months. So we had identified some algorithms to potentially identify malicious DNS records. We are now owner of our own tiny little data sets of DNS records. We have a good variety or mix of DNS exfiltration and tunneling software, and we achieved quite high accuracy and computational speed. But of course, there are some hurdles for the future, like defining and integrating this feature completely and seamlessly into our solution. And of course, as you already have seen, we have a 99.97% accuracy. This easily piles up to many false positives. So we have to integrate a little bit more time-dependent information to reduce those numbers even more. And of course, we are interested in the possibility of DOE or DOT. So maybe we have something in the future to present on this topic, and then we would love to present it here as well. But this is something for the future. Closing the loop, can we prevent data theft? I think we are not already at the finish line, but we are closer to it, and I hope that we are on the right path to prevent it a little bit, or to prevent data theft more sufficiently. But there are already some tasks which we have been doing and which needed to be done. And yeah, that's from my side. I hope I managed to stay within time. Yeah, looks good. That's it from my side. Thanks.
Fantastic. Thank you, Daniel. Okay, so I'm conscious time-wise, a couple of people had to drop off, but for those of you that are on the call, have you got any questions or comments for Daniel?
Hello?
I think I've lost Andrew.
Can you not hear me? Hello, can you hear me, or have I gone?
Did I drop out sound-wise then, people? Hello, can you hear me now?
Just try again. Oh, you can. Oh, okay. You can hear me, but you can't see me. How strange. Ed, does anyone have any questions for Daniel? Give you a moment to think. If not, I think we'll say that was an excellent presentation, Daniel. Do appreciate your time going through that. I think people might need to just review the material and potentially come back with questions when they've had a chance. Oh, sorry, there is a question from someone. John, do you have a question?